Okay. I am now recording. I have asked my students to be good for the recording. They have agreed. Right? Okay. So, this is a new model I've never used before. It's called Concept Attainment. I'm going to put some examples on the board that follow the definition I'm trying to get you to build. And I'm going to put some examples on the board that do not follow the definition I'm trying to get you to build. Okay? So you as a class are going to come up with something, but you're not going to blurt it out. Even if you figure it out pretty quickly, I don't want you to blurt it out because I want to let everyone kind of have that moment where they figure it out. Okay? So we're going to start on the yes side. So I'm going to give you something that is yes. Then I'm going to come over here and I'm going to give you something that is no. Okay? So on the yes side, we have a graph. Right side, we have a function. Not making any guesses. I don't want any guesses. I just want you to kind of analyze what this is like I just did. So, give me something. I want you to analyze what you see. Give me something else. Right? Understood. He's not allowed to talk now. Or X is a no. X is a no. Like, better than like X is not allowed. I don't know. I'm not answering any questions. I just want, that's what I want. That's absolutely what I want. So, keep thinking about that. What he said and what he said. Yes, ma'am. Say it a little louder. Let's take a poll right now with my yeses and nos. How many people think they have it figured out? Huh? Okay. Let me get a sideways. I think I might have it figured out, but I'm not confident at all. And then down, I have no idea what's going on today. What class period is it? Great, great. Okay. So right now, we have a graph. We have equation of a parabola, and then we have squared plus 9. Okay, and over here we have a graph of a parabola, an equation of a parabola, and x squared minus 9. Okay, I'm gonna give you something else. What do we think now? What would you like?
On the left side, there's more.
Anybody else want to add to that? Lateral numbers. Heard that before. Okay. So, you think you would benefit if I gave you another graph? Give you another graph. I changed that based off what you guys are saying. We need some more information. I would type up or write some stuff that you guys know or need to know. So let's. This is just not. Yeah. So tell me some things, we're gonna start forming this definition. We're gonna define whatever word it is or whatever concept it is on time. Fairness rate. Fairness rate. We're gonna start with definitions. Alright, open up. Okay. Is this on the yes or no? Not yet. Yeah. Okay. Letters.
All on the left.
Okay, so what we have so far is our yes side is imaginary numbers, positive and negative behaviors, axis. Degree of 5. Neither even nor odd. Lateral numbers, and they have at least one imaginary solution. Okay? So what we're going to do now is we're going to use the no section, and we're going to see if we can erase some of these because they might apply to the no as well. So are there any imaginary numbers? Right. Discuss it. X plus 2 squared, does it have to have imaginary? It's gonna bounce, so it's gonna bounce off the x-axis because it has multiplicity of 2. Okay, but we're still kind of iffy. Let's move down past that one and go to positive and negative end behaviors. This one has only negatives on the graph, but these are positive. So what do we think about that? Does that apply to both? I think that one applies to both. So we'll take that one off. Okay. Not down to the x-axis. We're going to expand on that. I don't really know what that means. Not down to the x-axis. Like this one doesn't touch it. Yeah. Okay. That's okay. No, I like it. I mean, I think it's kind of similar to another one on here. Let's skip it because we're not sure about what that means. All right, degree of 2 and a degree of 5. 2, 2, 2, 5. Yeah, that one's 5 also. 2, 2, 2, 3, 5. What do we think that tells us? Yeah, they both have degree of 2 and degree of 5 in them. So we'll go ahead and erase that one also. What does that mean even or odd? One is odd on both or on the left? On both. Let's see if that's not affecting your yes or no. Lateral numbers. What are lateral numbers? Imaginary numbers, which we already have on here. So we'll leave that. And at least one imaginary solution. Is that on both? Where? Where could there be an imaginary solution? This one's going to be X plus 0, yes. Okay, so x squared plus 9 equals 0 is going to give us, okay, so say an x squared equals negative 9, and then you take the square root and you get imaginary. Yes, ma'am. Would it be if the function is no sign of both on the graph? But then these are all positive. Over here, we have positive, positive. Oh, I don't have any negatives over here. That's a good point. Let me fix that. Okay. There's one. But that's a really good catch. That's good. And that's what I'm supposed to be doing. I'm pretty sure that's the way this works, that you tell me something and then I say, okay, can I debunk that for you? So that would be, this would be a yes. And it has a negative. I think I'm good with these four things. So let's see if we can form some sort of definition in better words than this using these four things. Say that again. Numbers. I like it. Okay. What's what do you think that's what I want to do to see? Polynomials are better numbers? Where is there an imaginary number here? Okay, you're saying if you pull this graph out, you can see it in the third dimension. Okay, that's not a number, that's a. It's not a number, that's a hallucination. Yes. Okay, he just said something really crucial to what I'm trying to get you to see here. He said, on that one up there, if we had an x squared up above the x-axis and we wanted to pull it out and see in this third dimension, you could see the imaginary number or x-intercept. Like he corrected himself. Think about that for a second. It does. The imaginaries do. And what are you saying? It does have imaginary numbers involved, but polynomials with imaginary numbers, what does that even mean? Like, where are those imaginary numbers? Solutions. Yeah. Not bound to the x-axis. That's what we're saying, is that it can have solutions that are not on the real axis. Yes, is what I was trying to do. Polynomials with imaginary solutions. So let's talk about these examples that we had. How do we know this one and this one? These are two graphs. How do we know they're going to have imaginary solutions? How do your own graph?
Okay. So it's two zeros.
Not you, but it has to have two zeros because it's x squared. But how do you know? Like, justify. Okay, but could be you have two factors or you have to square root it, you're going to get two things, but how do you know that's the thing? How is that solidified for you? That, oh yeah, the degree is 2, so there's 2 solutions. But how do you know that? I mean, what is the fundamental learning that you have to know in algebra? Oh, wait, you hear him? You hear him? Sorry, I cut you off, Bruce. What's say it with me, the fundamental theorem of algebra. Then there has this does not have two real zeros, and we know that. So it must have two. We also call that complex solutions. Okay, so we're talking about complex numbers. Solutions. So, in actuality, complex numbers are any number that can be written in the form of a plus b. Okay, do you remember this? Any number that can be written in the form of a plus bi. Right now, we're going to see if we can identify numbers written in the form of a plus bi. Ready? Number 1, 2 plus 3i. Is this a complex number? Because it's written in the form a plus bi, where a is, and b is, and I is the imaginary unit. Yes. Okay. It does have to be I, because I is a specific imaginary unit, like pi is a specific irrational number. Okay. Try again. Ready? 42